that it's compatible with. Okay, then what is going to happen? I look at omega naught, I act it on J naught. So remember, sorry. Oh my God! I thought. Okay. I really freaked the hell out of me. I thought there was a person standing behind me.
It's only you.
Yeah, the scariest of all people. Yeah. Okay. So okay, that has really unnerved me. Okay, just give me a minute. Okay.
I'm really sorry. I didn't want to disturb you.
I thought you started playing the match or something. Yeah, let's just watch the match. Okay. So J naught is already compatible with the standard structure, and I'm assuming J is also compatible. So what can I say about this? I mean, there's linearity, right, over here. So I already know that this is positive, and I also know that this is positive. So if I add these two, this is positive for all non-zero u. What does that tell me about? Why am I writing this? If I have this example. Yeah, so that tells me that the kernel of this has to be trivial, right? Because this is non-DJ. If there was something in the kernel, then that was something non-trivial in the kernel, and this wouldn't hold. So that tells me that if J is compatible with omega naught, then J naught plus J is invertible. I'm really working at the level of matrices right now, so just forget sort of the bundle structure. It's all on CN, and so that's what I'm doing. Okay, so the final fact that I will state, and then we will actually try to give you a sense of this proof. So if I take this map, J going to, what did I set up? I had J naught minus J. What is this? J naught minus, so AJ. This, so there's more than bijectivity over here. These are both coming from spaces of matrices, so I can actually think of them as differentiable manifests, but let's forget about that. Is a bijective correspondence. So this is the space of compatible, almost complex, let's say matrices. So compatible with, okay. And on this side, we get, so you get all A in, so I can think of them as 2n cross 2n real matrices. They are going to be symmetric, which is something we already saw. They are going to be antilinear. In the operator norm, they are going to be atmospheric. So they're going to be the unit ball in the space that we wrote down earlier. Okay, so that's where this condition. So Amardeep mentioned that the Beltrami equation, the solvability requires a condition on A plus IB, which was missing in our picture. The point is that we cannot work with an arbitrary complex structure. We need some condition. We assume that it's compatible with respect to omega naught, and that tells us that whatever this matrix A that we get, it has a bound on its norm. Okay, so I'm not going to discuss this. These are not hard proofs. The thing is that when you write this like this, it does seem like a lot of language, but this is some space of matrices. This is some space of matrices. You can actually test all of this by hand. The main point of all of this is that if I do now want to produce a pseudo-holomorphic disk, rather than solve df composed with J naught is equal to J composed with df, I'm going to solve the Beltrami version of it. Okay? And I'm actually not going to solve any differential equations today. I'm just telling you what goes into, like, what kind of math goes into this. Yes, please.
Going back to Amardeep's point.
Sorry?
Going back to Amardeep's point.
Yes.
What exactly is the norm A less than 1 capturing in terms of J?
I think it's basically telling you, I'm sorry. Yeah, you won't get an I mean, when is this a Riemannian metric? You need a positivity
You're going
condition.
into that side. If we want to stay on a symplectic side.
I think it's the same thing that sort of the balls in that matrix have to be ellipses. It's the same idea. So here,
Not screwing up the structure.
yeah, exactly. Like here, for this to be Riemannian, there's a condition on EFG, and if that condition wasn't satisfied, then you would get like hyperbolas or something like that. So it's just like an eccentricity for conics kind of a condition. Yeah, that was what you were saying as well. Okay. So maybe I directly state. Yeah. It's a very good question. So actually, I'm going to write down the first black box, and so that maybe will address your question. So the equation will become. So maybe it's worth saying something or something. What you just said. So what will happen is, oh, I'm sorry. So what I want to say is, I want to call this space theta. Okay, the space of these matrices which satisfy all of this. And another thing I want to say over here, which maybe deserves a little space here. So in an arbitrary dimension, if I write this, then that also reduces, is equivalent to writing that Fz bar is this now n cross n. Okay. So this is always a little bit annoying. So I'm going to write this as a real, view this as an R2n vector. And this is really going to be A of J, Fc conjugate. And this is going to come from theta. Comes from theta if J is compatible with omega. Okay, so here this is all happening on Cn. We are completely, forget about an arbitrary capital M, we are completely working within Cn and the standard symplectic structure. That's all we care about. There, if I give you an almost complex structure that is compatible with the standard structure, then solving an equation like this is equivalent to this, which is a vector valued Beltrami equation. And there isn't like an extensive study or something like this. What is maybe something I want to mention is that Bromode's origin, I mean, this is there in many references, but there is a paper of, if you want a nice clean proof, then there's a paper of Sukhov and Tumanov, which basically proves Bromode's theorem, and it kind of solves this Beltrami equation using actual integral operators. So what they do is they do this clever thing where instead of working with a cube, okay, so what is the problem? You want to solve something like this, and then you want that the boundary values go and attach themselves to this cube. I'll come to that. But that's kind of a non-linear boundary condition because you have a circle over there. So they actually first apply a symplectomorphism and make this a cube over a triangle. So that's piecewise linear. And then there are some, people have studied some singular operators where you can solve these Beltrami equations when the boundary data is piecewise linear. So they are able to do that. So this is it's much more, I don't remember the date now. So they set it up like this. So now they have some vector value Beltrami equation for which there isn't like a general study like there is for one variable. But they use similar techniques, do some trick, and then they're able to find solutions. Okay, I'm not going to go into this piece at all. In fact, I'm going to take the solvability as a black box, but let me write down. This is Alexander Sukhov and this is Alexander Tumanov. But the E is French E and American E, I think RE and ER, right? Yeah, but they're both Russians. So You must know Tumanov quite well,
Yeah.
right? Yeah. So Sukhov has a whole bunch of papers with Tumanov and also with Ivashkovich, who you would know really well. So they have been sort of playing around with Gromov's ideas and doing this in like almost complex manifolds or sort of rewriting various proofs in accessible ways. And the reason is that Gromov's original proof, it's a little bit more complicated in that he considers what are known as moduli spaces of pseudo-holomorphic disks, which is already too many words, and then he proves this thing called the Gromov compactness theorem. And so, which is also all very nice, but if you want a quick accessible proof as a complex analyst, then I would recommend this particular paper. All right, so let me write down what the solvability, also let me pause. I mean, there's really no point sort of moving ahead. So if there are any, I'm also happy to repeat anything. If there are any questions. Okay, so if none of this made sense, it doesn't matter. We can go back to this. Where we are trying to put this ball inside this cylinder in a way that our map, you pull back the standard structure here, then when you pull it back here, you get back the map. Okay, and it has to be an embedding. It has to be a smooth embedding. That's what we are trying to do, and we are going to show that this is if this happens, then capital R is less than or equal to 1. So let me give you the first black box. So suppose A from, so remember sigma was my cylinder, which is B cross Cn. So suppose A from Cn to this space of sort of acceptable matrices. So these matrices are going to capture the compatible or most complex matrices with respect to omega. So suppose this is a smooth map that vanishes outside a compact set A in this tube. Okay, so I have this tube and I have some compact set here K, and I want to, at each point, I want to select a compatible complex structure. And what I'm saying is that A is 0. Oh, I'm sorry. Yeah, it vanishes outside K. So what does it mean for A to be 0? When A is 0, what structure are we looking at? Standard structure. Okay, so do not forget that. I'm sorry that so much gets lost when you do all of this. A is 0 precisely when J is equal to J naught. Okay, so when I'm setting A equal to 0, I'm just saying that I'm making some choice of complex. I have a compact set. Outside of that, my complex structure is going to be standard, but it's going to be non-standard inside K. That's the purpose of capital A. And if you're worried about this, I mean, this is Cn. What the hell is this? But this is sitting inside a space of matrices, and in fact, it's sitting inside, I think you can compute the dimension, I think it's n times n. So you can view it as sitting inside some Euclidean space. Okay, so this is not just some nonsense that I'm writing over here. Okay, so I have this selection of complex structures that vanishes outside a compact set. Then, for any P inside this cylinder, there exists a pseudo-holomorphic disk. Okay, so let me write it again. Pseudo-holomorphic disk F from B to Cn such that, let's write down all its features. 1, F is smooth up to the boundary. 2, the image of the disk. So the closure sits inside the closure of the cylinder, and the boundary maps to the boundary. The boundary of the cylinder is actually just the boundary of the unit disk plus Cn. So this disk is attached to the boundary of the cylinder. We chose a point. Okay, this is not just, I've chosen a point and I want a pseudo-holomorphic disk going through P. So I can normalize and ensure that the origin gets mapped to this point. F of 0 is equal to P. And I'm going to write one more statement which I need to explain, which is that the area of this disk, what is that? The area of F is pi. I haven't quite told you what it means to be the area of a pseudo-holomorphic disk, But let's just stare at this black box for some time. The most important thing is missing, which is, no, it's not missing really. So maybe I need to explain this. So when I say this, it really just means that phi fz bar at fz bar satisfies A, and of course A at which point, at which f gets mapped. This is what I mean by pseudo-holomorphic. So it's pseudo-holomorphic with respect to what structure? We are choosing a global structure on Cn. And at each point of Cn, I'm giving you an almost complex structure. So if I evaluate fz bar at some point z, then I look at where f of z is going. I pick the particular matrix over there. That's going to be the structure over there. And I satisfy the vector value Beltran equation with it. This is just this statement. It's pseudo-holomorphic with respect to this structure that we have chosen over here, which outside K, this is 0. So outside K, if you look at this disk, once I exit K, it is a genuine holomorphic disk. Okay, so in this piece and this piece, it is a genuinely holomorphic disk. Inside, it's holomorphic with respect to something, some weird thing, whatever that is. Okay, so this is a little bit annoying because even though my structure is standard, I'm having to go via almost complex structure. So why is that? So we will see momentarily the proof, but I still have to explain to you what the area is. Questions? Please stare at this for however long you need to. And if you like words, lots of words, then this is a quasi-linear elliptic PDE, and we're looking at a boundary value problem for a quasi-linear elliptic PDE, okay? But, so which, if you know anything about elliptic PDEs, this part should not surprise you, because I described pseudo-holomorphic curves as being C1 smooth, but then you're somehow able to amp up the smoothness to C infinity. So that is known as elliptic regularity. And if I have time, I don't know how I'll pace these lectures. I did want to give you a sense of how that works in a very special setting. So we will come back to, hopefully we can see something like this. I will also stick to my promise that once this lecture is over, we will never talk about arbitrary almost complex structures. Okay, we never mind. We'll go to our standard Cauchy-Riemann, our favorite Cauchy-Riemann equations. Okay.
Going back to the think about doing out of holomorphic structure to have something holomorphic. So I want to extremize something at some point.
You're saying, why am I going to the space of almost complex structures? No, so in some sense, some extremizing is happening somehow under the rug. But what's going to happen is that once I map this, and that map, see, the map is just a symplectomorphism. It's not a biholomorphism. So when I push forward this structure, it's going to give me a new structure. So see, if I could somehow get a biholomorphism, then the biholomorphism, so okay. I don't want to say too many things which confuse people, but the point is that I'm going to go via contradiction. I'm going to assume there is a symplectomorphism. Okay, so symplectomorphism is good at preserving this structure. But symplectomorphism is not going to preserve J0. Why should it preserve J0? So it's going to do something to J0, and that's going to give us a new structure over there, which is not necessarily J0. So we'll have to deal with that. That's where it's coming from. Okay, and we'll see it very shortly. I will write all of this. So there are no. So we will very quickly talk about area, and maybe this is a good opportunity for me to give you an exercise as well. And maybe I will take the exercise. So if the definition, sorry, but these are all needed. It's from to, let's just say Cn omega naught, but it has some structure J. Is a J holomorphic, a pseudo holomorphic this, then area of F of this disk is also sometimes known as the symplectic energy. It is also known as the Dirichlet energy. You will see why. All you do is you pull back omega naught. You can do this for any symplectic manifold, but let's just stick to this. So this was a 2 form. I pull it back, I get a 2 form, and I can integrate a 2 form over a 2 manifold. So this is the area of that. Okay, so it's just that, yes. For this one? Here there is no boundary condition. For this we are asking that the boundary of the disk.
Has to lie. We are not fixing any.
We are not fixing manifold. Eventually they actually sit inside certain Lagrangian manifolds there. So this is by itself just a symplectic. The boundary is just some sort of symplectic object. So there they do go and attach themselves to certain special things. But we actually, for the purpose of this proof, that really doesn't matter. It just has to. Okay, what does matter? And there's so much to say, but so little time. So we will come to that. The thing is, it is important for them to go all the way to the boundary. And for those of you who studied proper maps, you know that makes sense. It's going to make sense from a certain area point of view. So if we don't go all the way up to the boundary, this proof will not work. So if I get the chance, I will indicate exactly where that is playing the role. Both these, by the way, the fact that I am not just going to the boundary, I mean, if I just take the standard structure, I mean, of course, there are so many disks, right? So I'm also anchoring the disk to a specific point, and I'm taking it all the way to the boundary. This is good information. Okay, so I pull back this form, I get this quantity, which because I have taken the standard structure, okay, so maybe let me also say, maybe I will not say that here. I will say here. So if J is J naught, so if I'm looking at a genuine holomorphic disk from D into Cn, then when you work out the details of, when you write this down, so everybody has to get very good at pulling back forms and writing this in terms of, there's no excuse for that, okay? So I think we teach enough multivariable calculus, enough differentiable manifold theory that people should be able to compute with forms, okay? There's no point doing geometry if you can't do that. But in any case, I'm sure I'm going to make a mistake after giving that lecture. But what you're going to get, so if I write F1 to Fn in terms of coordinates, you're just going to get, because this is the standard structure and because this is holomorphic, we're going to get then of course there's a 2i in the denominator. Okay, so on each piece, you're just going to get absolute square of the complex derivative of that component, and then you just take the area of form in that particular component and you sum it up. Okay, this is just a formula, and this will be important later when I give you an exercise. So there is this is kind of an important object, and it's studied quite a bit, but we will come back to this. Okay, so now I can maybe finally the idea of the proof. You can also check that if I
That was the comment about Dirichlet.
sorry.
That was the comment about.
Yes. So anybody who's seen this word Dirichlet in the context of integration or energy, it's sort of the L2 norm of the gradient, right? So as I've studied the reduced Bergman space, that should I don't know, maybe doing spawn memories or maybe it's PTSD. I don't know. Depends on how that project went. But in any case, it's nice to see things pop up. Similar things pop up in other places. But what we will do is So let me go back to this picture. Let me create some space here, and then I'll give you the idea of the proof. So this is my ball to begin with, E and R. This is my cylinder, and I'm going to assume that you have a symplectic embedding from the ball, and it goes to some thing. Let's say the image is okay. So assume there is a there exists a symplectic embedding, capital P. From V and R, such that okay, there's nothing. I mean, it's just a symplectic embedding. Let G equal to the image. It's something into there. Okay. And now what I'm going to do is I'm going to push forward. So let's look at the picture over here. We have so where does this map go? So it goes from P, B, and R. This is BP. I've written this the wrong way. I don't like this. Okay, never mind. So I have then I have the J0 structure, the standard complex structure. And then I also have the inverse. So all I'm doing with these diagrams is I'm going to push forward the complex structure via D. So let J be, and J, I want it to go from PG to PG. So it's a complex structure on the image. And what this is going to be is it's just going to be the composition here. So BP composed with J0, composed with P. Okay, so check. These are both easy computations. First of all, you do get a complex structure. So if I just multiply these two, dp inverse and dp will cancel, you'll get J0 square and so on. So it's very easy. The second thing, which is a little bit more, but also a few lines, J is compatible. So remember, where is J living? J is living here. Okay, so capital G now has omega naught on it, and it has this capital J on it. Okay, and this capital J is compatible, turns out to be compatible with omega naught. So that's good because that's the kind of almost complex structure we want to do. So this the pushed forward structure is compatible with omega naught. The omega naught is always the same. We always work with that. And what I'm going to do is, so I will convert J to AJ. So I can go between, because of this compatibility, I can think of J instead. I can think of AJ instead of J. I can go between the two. So using a cutoff. So now remember that my complex structure has to be compactly supported, right? So I have to cut it off because this J is living. So I know a lot of you may not be able to see this picture. This J is living on this open set here, but I'm going to cut it off. So for that, I'm going to fix a small radius. Fix R positive, which is less than R, and sorry, I need to make sure I'm saying this correct. Okay, and so what I do is, and then I look at the closure of this smaller ball. I'm going to do my full analysis on that. So let's call it capital L. So colors, we need colors. So I take a slightly smaller ball. I take it. Sorry. Okay, I take the closure of that, and then I push it forward. Actually, I want to call this L. Okay, so let's call the image of this L. It's going to be a compact set. So all topological statements I'm going to leave for you to check. And so we are going to use, this is something I'm going to say verbally, I'm going to use a cutoff function so that capital J remains capital J here and gets killed outside. Okay, so I apply that cutoff function to A of J. using a cutoff function. This. And I'm simply doing this because the way my theorem is stated, it is stated for compactly supported data, right? A has to be compactly supported. So this data has to be compactly supported. So I need to make sure that that is indeed the case. So using a cutoff, which is a very standard procedure, we obtain a smooth selection of almost complex structures on Cn such that, oh, okay, there's a piece missing here, but I'll come back to that. It's not a big deal. So such that support of A lies in the tube, and on L itself, so A of J, so A coincides with A of J on L itself. So on L, I don't disturb the complex structure. Whatever this capital J I'm getting, I keep it like that, and then I use a cutoff to cut off A outside this tube. By the way, here one also needs a condition on, so when it lands in theta, the norm is less than 1, but I actually need a little bit less. I mean, I need to assume that there exists a less than 1, so that the norm of A is actually strictly less than A. But because of compact support and all, we are going to be able to ensure it. Don't worry about this too much. The solvability is not of concern. Okay, so what do we have? So let's look at our picture. So we have now set up this object over here, and we apply the theorem. So apply black box. Apply black box 1, 2. What do I apply? Okay. So let's see where the origin goes. The origin goes to some point of the ball. Okay, I'm going to apply it to that. So let P equal to the image of the origin of the ball. Important. This is important actually. So apply dp1 to this A and B, this choice. So let's look at the picture. What do we get? That means we are going to get a pseudo-holomorphic disk. And I will draw this picture carefully. So on this side, my two-dimensional disk is going to be drawn as a curve. Okay, so it's going to pass through P. Picture is important. It's going to be attached to the boundary. It will enter this yellow piece. It may exit this yellow piece. It may enter it again. Go through P, like do all sorts of things, and then go back. Okay, so this is my, when I apply the black box, I'm going to get a pseudo-holomorphic curve like this, passing through P and touching the boundary. Let's see what's happening here. Okay, this is the image of a disk. So what may happen is that because of this entry and exit, you may get something so when I pull it back, so the whole thing is some sort of a disk. Okay, so it could happen that in the end, when it goes outside, it's kind of attaching in a nice way outside. And here it maybe is just looping up by itself. But I'm only interested in the portion that is going to intersect this yellow ball. The yellow ball is a ball of slightly smaller radius. So there it may have many boundaries. But then later it exits out. And maybe what happens is when it exits out, this is just one piece over here. I don't want to draw that.
Can be disconnected, right? Because
yeah, it can be disconnected also. You could get some little piece like this over here. Okay, you could get a little piece like that. So, yeah.
As you go through 0 now, like, you're at P.
I'm taking 0 to P, so the disk is all of this. So it does go through 0.
Okay.
Yeah, sorry.
I'm understanding the picture.
Yeah. Yeah, so here the disk is one-dimensional, here the disk is two-dimensional. It's actually the surface that we get. I haven't thought about connectedness, but yeah, presumably, I mean, there's no reason to assume that you will have a connected piece. I think it's fine. I need to think about this a little bit, but I think it's fine. Yeah, it's not a problem. Okay, so I get this piece, and just to have our picture, I would like the notes to be completed. Anyway, I'm not going to pay attention much more. So, nice job. Okay, so there exists J holomorphic, and this J really refers to this A, this cutoff A. There exists a J holomorphic disk F from B to this sigma, actually the closure to sigma closure, such that f of 0 is really capital P of 0, which is P, and all the other properties. Okay. Also, the area of F is equal to pi, and other desired features. What are the other desired features? That the boundary maps to the boundary of Q. Okay. And now what we do is, so remember that, so I think the picture will help. So I have ball, I have tube, and I'm mapping, and so my J holomorphic, oh sorry, people probably can't see this. Okay, so I have my diffeomorphism, which I'll maybe write in the opposite direction, P inverse, which is like this, which is going from G, it's not going from the tube. So I have this small f, which is going up here. It is J naught J holomorphic, and what I will do is I'll actually pull it back here. So I will take P inverse of F. Right? So I'll go here, I get this pseudo holomorphic disk. I look at the portion where it intersects this ball, and I get something here. This you can check. So if I look at this new map, let's call it F tilde. This is holomorphic from, so classically holomorphic from this. Okay, so here you are getting something which is J naught comma J holomorphic. But once you compose with P inverse, you can check that this composition will be holomorphic in the classical sense. And the reason for that is because this J, on which piece? Okay, so this is something to be very careful about. Let me go back here. So on the yellow piece, we are still working with the old J. Okay, outside yellow J, we don't know, we've cut it off. So we have to be careful. We have a disk, we've sent it, and let me draw the disk in blue. We have this disk, we've sent it up here by a small f, and then I want to push it forward. So my claim is that it's not everywhere, but if I look at P inverse of F restricted to just L. Okay, remember that capital L is where we have the pushed forward structure. Outside capital L, we have no idea what's happening. So J was the pushed forward structure on capital L, which means if I push it back, I'm going to get the old structure here, J naught, right? J is obtained by pushing J naught forward. So if I push J back, I'm going to get J naught, just simply. But that happens only on the yellow piece, because outside the yellow piece, we have messed up J, so we don't know. So on the yellow piece, this is true holomorphic in the classical sense. It's true holomorphic.
Thinking about F inverse of that. It should be on the disk, not on the.
And of course, you might ask, what is F inverse of L? And please don't, because I won't be able to answer right now. But that might give. So I don't know what F inverse L looks like. But you have to argue that it's actually going to look like some sort of subdomain, possibly with holes. It's going to look like some region inside this disk, which you can topologically argue has some nice structure, which I'm not going to go into. You're absolutely right. So I pull the yellow part back. I get some region here. Now I take the composition, I restrict it to this yellow piece. I get something which is truly holomorphic. living inside the yellow piece, going all the way up to the boundary, because this blue disk was going all the way up to the boundary, so it has to exit the yellow piece, which means just this blue part has to touch the boundary of the yellow part. And here's another black box that I'm going to use. So hang on. Sorry, I know this is
The outside boundary is kind of the last point time when it exits this.
yeah, it's kind of the last time when it exits the region, the yellow region. Okay, so let me just make one point clear right now. So, okay, so the punchline is important. So let's write down a few things before we finish this. So let's call x. What is x? It's going to be P inverse of f of x. So lots of letters, but what it is, it's exactly this blue region in the picture. Okay, I'm only looking at the blue part. That's capital X. This is a complex curve in the ball with boundary on the ball. By the way, this is the smaller ball. Okay, that's the whole point. The point is that I wanted to make J compactly supported. So, right. So I wanted to, so I shrunk the ball a little bit, and now I pull back this yellow piece, which has now here become the blue piece. And this is what I'm calling capital X, which is a true complex curve with boundary, and the boundary is sitting on this ball. Okay, and here's black box number 2, which is a really nice statement, for which you can, classically you can look at, because there's a really nice book called Analytic Sets. This is a very general statement. Whenever you have a complex curve whose boundary is sitting on the ball like this, then the area of this complex curve, what does the area mean? Well, it's going to be the same thing that we get from that. It's always at least. So if somebody gives you a ball of radius r, you look at the equatorial disk. There are lots of one-dimensional disks. These equatorial disks are going to have radius at least pi r square. Okay, so any such complex curve must have area at least pi r square. This is quite an interesting fact. And as an exercise, what I'm going to give you is that here's a nice exercise. Suppose you have something which is going from with this, but this is holomorphic, continuous up to the boundary. Then show that if I in fact pull back, I give you an expression for this. If I pull this back, then you actually get this. So here the problem with our capital X is that it's not the image of holomorphic image of a full disk. It's the holomorphic image of some weird yellow region here. But I'm saying that if you're in the good situation where your curve was actually the holomorphic image of a disk, so assume it's proper. So it goes to the boundary, okay? So assume that the boundary. See, if the boundary doesn't go to the boundary, you take a ball and you can take small, f of 0 goes to 0. You have to fix the center of the ball. Okay, so of course I can take these things, but the problem is if I have to go through the origin, and if I don't go through the boundary, I can take smaller disks like this. They are not going to have area pi r square. So the fact is that I'm going through the origin and I'm going all the way through the boundary. That forces the area to be pi r, at least pi r square. Okay, it's both those features. If I was not going to the origin, I could have taken disks like this, closer and closer to the poles. And if I'm not going to the boundary but going through the origin, I could have taken disks like this. So both features are important. Every curve. There's no holomorphicity needed. Okay, then prove that. Or produce for me another exercise. Produce for me a smooth, just say smooth embedding of the disk so that the area. See, the thing is, how do you define area? That's the key over here. So the area, I'm using the complex structure to define the area. That's the idea. But even with the Hausdorff, I mean, if you take Hausdorff area, try to produce smooth disks whose with less than pi r square. And it's a nice exercise actually. I don't know if it's true or not. It must be. I mean, without any.
Implies the disk.
Sorry?
Equality implies the disk.
Equality implies that you have these affine pieces. Yeah. Absolutely. Yeah. Very nice. Okay. But where are we? So sorry. Yeah, pi r square. This is correct. Okay. I'm not going to do this little piece. I didn't quite use all the, by the way, so this guy X, it does contain the origin, okay? Because the way we constructed this blue piece, notice that P is there. So when I go back here, I'm still going to get the origin. So phi inverse of F is going to contain the origin. The way I've arranged it. So that's important, okay? The fact that 0 is in there is what allows you to say this.
In the exercise,
Yes.
When we extend it to the boundary, is the boundary sitting inside the
Yes,
boundary?
yes. So proper will tell you that the boundary has to go inside. That is important. So this is capital R. Let's make it smaller. So just do it for things on the disk. Then we can worry about the things. And more words, because I like words. This has something to do with fact that complex curves are minimal surfaces. So this is actually something which is about minimal surfaces. But okay, so we are almost done. So I didn't quite use everything. The disk I constructed had area pi. Okay, and this blue piece is small. The blue piece intersected with the yellow piece is smaller than the full blue piece. So its area is going to be only smaller. And this is a symplectic map. Symplectic maps preserve areas. And so that means this blue piece is going to have area less than or equal to the full blue piece. So this area is less than or equal to pi. So that tells us that small r is less than or equal to 1. But this was true for an arbitrary small r less than capital R. And so that tells us that capital R is less than. Now, we're finally done. Okay, after a lot of work, which we didn't even do, like, two of the most important results are black boxes. So you can see how powerful, you really need to do a lot of work to prove something which is actually very, it's so simple to state, and it's very beautiful, it's very concrete objects, but it's a lot of work. So I think I was able to make the few comments over here that I wanted to, which was addressing the questions that Amardeep had asked about boundary going to boundary. That's definitely playing a big role. And maybe one thing I will, I know it's been a lot of work and time, but I did want to stick to my promise of, actually maybe I will break my promise. I will have to talk a little bit more about symplectic geometry on Monday, just so that I don't want to, but it's going to be very brief. We're not going to do any computations. If you're really interested in this, let me say this is chapter 3, section 15. This all goes back to Lelong and actually has to do with Lelong numbers. So some of you may have heard of Lelong numbers. So it has to do with that, but I will not go into that. Let me see if I have any more comments. So, okay. So the point of these 2 lectures was to tell you that there are all sorts of problems in which attached analytic disks arise. And what is beautiful about them is that you're able to do something in higher dimensions, in almost complex manifolds, by reducing everything to one variable theory. That's the whole advantage of working with disks, right? So even a problem like this, this is a good exercise in one variable complex analysis. Okay, fine. You're mapping in Pn, but you really just look at each component. Each component is holomorphic, and you just use that. So this basic exercise, which is at the heart of one of the 2 things, and even this, like I said, can be solved using some variation of the classical Beltrami equation. So these are all one variable results, and we are using them in this kind of a neat way. So that should tell you that we should have some expertise in being able to construct disks. What goes behind it. And as I promised, I want to tell you how to be able to do something like this. I don't want this added headache of a Beltrami type of operator. So we will go to the setting where our structure is standard. We will be working with the classical Cauchy-Riemann equation. And then the question that you asked, what is the boundary value? condition. That's going to play a big role, and there I'm going to work with totally real manifolds, which I will tell you a little bit about before we go. Okay, so I think let's stop here and we'll resume next week. This area? Yeah. So this area has nothing to do with anything we have set up. We are just using the fact that capital X is a complex curve in the wall whose boundary is on the wall. This is an independent fact about complex curves, and you can check how long and a little bit like this existence. Okay? So, no, because now our region is not the disk, but you sort of can generalize this when you can take this to be, let's say, a subdomain of D with finitely many. So maybe we can assume these have smooth boundaries. Okay, so it doesn't follow directly. This is a toy case, but this piece is completely independent of the entire discussion. This piece is coming from the symplectic discussion that we constructed this disk to have area, because that's hidden in there. Make sense?
It should work for